Welcome to ECE 3270, Introduction to PLC Programming, Lecture 4. Today we're going to be talking about timers and counters. So there are ways to get around using the timer and counter structures, but they make the world a lot nicer, and we're going to be going over how to use those in this lecture. But first, as usual, we'll start with an industry connection video. So we've previously introduced bit latch sequencing. However, bit latch sequencing and other methods of sequencing are not going away for the foreseeable future for you in this class or for industry at large. It's important to be able to do things in a specific order, and bit latch sequencing makes that possible in a PLC where maybe you don't want to use some of the other sequencing techniques. Bit latch sequencing is a very good way to go about making things happen in a specific order. So in this video, it's another view of something we've already looked at, but another view of the same process. However, in this video, the sequence has been polished significantly and everything's running much smoother. So what we're going to be noticing here is how everything happens in a very specific order, and that order is non-negotiable, and the PLC has to impose that specific order on the operations in the station. And when we have a specific order that we want things to happen in, a lot of times the best way to go about it is a bit latch sequence. So for looking into exactly what a bit latch sequence is, that has already been talked about, and you should have had some familiarity with it at this point. But this is reiterating the importance of those, and it's a signal that you might be using them again in a coming exercise. So let's look at this video. So we have a pallet coming into the station. The pallet had to race first, then the robot has to get the gear, then the robot has to get the bearing, place the bearing, then the press can press. That has to happen in that specific order. Then the robot moves the part over to the testing nest. Then it's going to offload some more parts from the pallet to stage them for the next pressing operation that's going to happen in the next pallet. All of this has to be in this specific order. That's why the robot's having to wait here. The PLC said, wait for your next operation. Done. Removing the last part from the station, back to the pallet, release the pallet. So everything you saw there happened in a very specific order, because it's sort of like when you buy furniture from Walmart and it says, you must adjoin leg B to part A before you move on to install the brace or something like that. And then you decide not to. And then you realize that actually, you can't put it together unless you do it in that specific order. That's exactly what we have here. This stuff doesn't go together in whichever order we feel like putting it together. It has to be done in a very specific process. Not only that, but there's things behind the scenes happening in a specific process too. Behind the scenes, after a pressing operation is complete, the PLC has to send the data about how far it pressed the bearing onto the gear and with how much force back to the database. So that has to be saved to the database, and there's an order that has to be imposed to how it transmits information to that database. So everything has to be done in a highly specified order, and when that's the case, we use bit latch sequences. It's also pretty helpful to be able to use timers in those sequences, because let's say, for instance, when the robot comes over and drops off the part into this nest back here, there's a sensor right here that shoots this red beam across you see reflected on this metal surface that's detecting the presence of that part. Well, little things can make those sensors flicker, and they can be on for just, maybe a millisecond. And there's not really a part there, just maybe, a particle floating through the air or something interrupted the beam. Well, if this was programmed poorly, and if we were not using any timers, then little obstructions like that cause blips in the sensors would be thought to have actually been real, real parts introduced. So if we just said, oh, something broke this sensor beam, there must be a part present, there would be a lot of false alarms. Because if a part is introduced back here when it's not expected, that can cause the station to go into a fault scenario. So there would be lots of nuisance faults and things like that. Instead, we don't just say, is the sensor on? We say, has the sensor been on for long enough? We debounce the sensor. And if the sensor is on for, let's say 100 milliseconds, then it's probably an actual part present in the station and not some, random blip. That's an important concept, this idea of debouncing a sensor. It comes up with buttons also. Sometimes you don't want the button to cause an action the moment it's pressed. What if, the wind blew very hard and it caused the button to slightly make the circuit, and it caused the sensor, or caused the circuit to look like it was being pressed? Or maybe even someone bumped it, like their shoulder bumped up against the button. Well, maybe we want to avoid those sort of things, and so we want to require that buttons are on for a certain amount of time before we'll take an action. Sensors are on for a certain amount of time before we'll trust them. That idea is called debouncing. So 2 things here that we're introducing and kind of hammering home. Number 1 is sequencing, and number 2 is debouncing using timers. Well, that's enough introduction and industry connection. Let's move on straight to talking about timer and counter instructions. So first of all, timers and counters are treated very similarly in Allen Bradley, and in most PLC programming environments. So much so, though, that Allen Bradley combines them into a single chapter in their ladder logic instruction manual. So chapter 3 is the timer and counter instructions section. These are all the various instructions that are associated with timers and counters. However, of these, you're only going to be using or need to use a subset. Count up, quite helpful. Reset. RTO, or retentive timer on, and then timer on delay. These 4 are going to be necessary for completing coming labs. The other instructions here have their place and are useful, but 95% of the time, if you need a timer or a counter, you're going to be using one of these. You're going to either be using a count up if you're using a counter, most likely. You're going to be using a retentive timer on or a T on, which is a timer on delay. With that being said, we're going to go through and discuss each of these. And hopefully you'll walk away understanding what each of them do and where and when to apply them. So the first instruction we're going to talk about from that subset is T on, which stands for timer on delay. The timer on delay is best understood to be answering the question, has it been long enough? So what this instruction does is take a preset amount of time, and when the rung in condition has been on for a time equal to or greater than the preset, the timer done bit will come on. So that should give you a general intuition of how this works. So if I were to use this in conjunction with a button so that I could have a debounced button, what would happen is I'd press the button, which would turn on the rung in condition here, and I would have typed into the preset a certain amount of time. And once I had held that button for more than that amount of time, this done bit will become true. So then this timer done is how I know that my button has been pressed long enough. That's why I say this instruction is helpful when you want to know, has it been long enough? That's the question this instruction answers. Now let's look at some of the formal documentation from the manual so that we can really make sure we understand what this timer does. First of all, notice there's a couple of operands involved whenever you insert this instruction into the program. So this is exactly what it'll look like if you insert this into the ladder logic software, and you have to provide each of these operands. Well, you don't have to provide the accumulator, and the preset defaults to 0. So technically all you have to provide is the timer structure. However, in general, you're going to want to set the timer structure and the preset. So those two you're going to have to provide. Accumulator you will never set. That would be an unusual situation where you would want to adjust the accumulator directly, other than to possibly set it to 0. We'll get to that later. All right, let's talk about what each of these operands are. Timer is a timer structure. So don't misunderstand me. There is a timer instruction right here called T-on, timer on delay. But there's a data type, just like bool or dent in Allen Bradley, called timer. And this timer data type contains information that is stored in it by a timer instruction. So you have to have a place more or less to store how long it's been. Is the rung in condition true? Is the done bit on? These sort of questions. And that place that it stores that sort of information is in a timer tag. So to be able to use a T-on instruction in your PLC program, you have to create a tag with the data type timer. You can name it whatever you want to, but the data type has to be timer. And then you have to give the name of that tag to this instruction in this specific operand. And then what it does is it will store the information for this T-on instruction in that timer tag. So we have to have a timer structure. Second, we're going to have to give it a preset. Preset's sort of an odd name. The preset is the target. It's how long it needs to be on before it becomes true. And the format, notice here, it says the format for the timer structure is tag. You have to specify a tag name here. You can't type in 5. You have to give it a timer tag name. The name of a timer tag in the tag table. However, the preset must be an immediate value. So whatever you type in here has to be an immediate value, and it's in milliseconds. So you can type in 100, you can type in 200, and 100 would be equivalent to saying, hey, I want you to time this up to 100 milliseconds. 200 would mean I want you to time this up to 200 milliseconds. And once it's been 100 milliseconds or 200, depending on which one you type in, then the done bit will come on. And then the accumulator operand is a preset value. I say preset because you're typing it in before the timer runs. But the preset, I shouldn't have said that. The preset is the target. The accumulator is the current value in the accumulator. And the accumulator is where it stores how long it's been. So the preset is the target, and the accumulator is how long you've waited so far. Both of them are in milliseconds. So if you type in 200 into the preset, that means I want you to wait 200 milliseconds. The accumulator is going to store how long you've waited. And once the accumulator is greater than or equal to the preset, done will come on. So I'll write that down. If the accumulator is greater than or equal to the preset, then .done equals true. Else. So hopefully that makes sense. Okay, so that's enough about the operands of this specific instruction. Now let's move on to the timer structure behind it. So we said that you have to specify the name of a timer tag, which will act as the place where this instruction stores all of its information. Well, here is the elements, the attributes of that timer tag structure. Inside this data type timer, there are the following things. A .en bit. The .en bit is used to store whether or not the rung in condition is true or false, more or less. So, and it says that right here, the enable bit contains rung in condition in when the instruction was last executed. So the last time the PLC scanned this rung, if the rung in condition was true, the .en bit inside this timer tag that you type in right here will also be true. If it was false, then the .en bit will be false. The timer timing bit .tt inside the timer structure is used to tell if the timer is currently running. So if the accumulator has met the preset value, the timer is no longer timing. Or if the rung in condition is not true, then the timer is not timing. So that's the timer timing bit, to see if the timer is currently running. That can be helpful sometimes. The .dn bit is true, as I've said, if your accumulator value is greater than or equal to the preset. So the preset's the target, and the accumulator is how long it's been. So done will be true if the answer to the question, has it been long enough, is yes. Done will be false if the answer to has it been long enough is false. And then inside this timer structure, you also have a .pre and a .acc. .pre is the same as the preset. So let's say we wanted to programmatically set our preset value. We didn't want to type it in to the timer. We wanted to have a line of PLC code to move a value into the preset. Well, that would be easy enough. All we would have to do is have a move instruction where we move 0, and let's say that the timer tag name that we're using here is my_TMR. So then all we would have to do is move 0 into my_TMR.pre. That's very small, but I think you get the idea. We can programmatically set the target value that we're going to time to by programmatically moving a value into this .pre attribute of the timer structure. We can access the current accumulator value through the .acc component of the timer structure, attribute of the timer structure. So this contains how long you've been waiting, and this contains how long you want to wait. And then finally, looking at the description for what happens when the rung-in condition is false versus true. If the rung-in condition is false, then the rung-out condition will also be false. The EN bit will be set to false, as will the timer timing and the done bit. And this is interesting, so notice this. The accumulator will be immediately cleared to 0. That's a little different than other timer instructions we're going to look at. So the accumulator for a T-on immediately returns to 0 if the rung-in condition is false. It does not store how long you've waited. It only stores how long you've waited as long as the rung-in condition is true. If the rung-in condition is true, then we are going to follow the flow chart because the explanation of execution is quite lengthy. So instead of looking at the flow chart, I have described it to you. If the rung-in condition is true, then the accumulator will begin to increment, and the value that is stored in the accumulator represents the amount of time that has passed since this rung-in condition became true in milliseconds. Once the accumulator becomes greater than or equal to the preset, timer timing will no longer be true, and done will be true, saying that you have indeed waited long enough. A quick reiteration of what I've said for the T-on instruction. So here is the timing diagram for the T-on instruction given by the Allen Bradley manual. So what we're looking at here is we have the rung-in condition becomes true, which causes the EN bit in the timer structure to be true, and it causes the timer to be timing. But the done bit is not on because we haven't waited long enough. The preset is set at this value up here, but our accumulator doesn't reach the preset value before the rung-in condition goes off. So this would be like someone pressing a button, but then they didn't press it for long enough for it to actually count. So this is when their shoulder bumped the button right here. It's just a really short pulse. They just ran into it by accident. So the good thing is we didn't say, hey, it's been long enough, right? Because we left the done bit off. So our preset was set long enough that we weren't detecting those sort of bumps. But then over here, we kept going, and someone very intentionally pressed it and held the button in. So notice what happens. The EN bit, which is a part of the timer structure, which we typed in right here, becomes true. The timer timing becomes true, but notice it doesn't stay on for as long as the EN bit does. The EN bit, the enable bit, is on as long as the rung-in condition is true. But the timer timing is only on until we meet the preset value. So as soon as the rung-in condition became true, we started counting how long it had been since the rung-in condition became true. And here we met the preset value. So if this was, let's say, 100 milliseconds. So from this line to this line is 100 milliseconds from here to here. And so our accumulator accumulated 100 milliseconds. As soon as it got to that set value, we didn't keep accumulating. We went flat after that because we were done. So the moment our accumulator met the preset value, we turned on done and turned off timer timing. And the done bit stays on, but we do not continue to accumulate, and we are no longer timing until the rung-in condition goes off. Notice, as soon as the rung-in condition is false, the accumulator resets to 0. So the whole point of the T on instruction is to answer the question, have you waited long enough? If you want to answer the question, how long have I waited, the T on instruction is not very good because it immediately clears the value as soon as the rung in condition becomes false. So if you wanted to have someone press the button, release it, press it, release it, press it, release it, and then an instruction tell you how long total the button had been pressed, T-on's not going to help you because each time you release that button, it's going to return to 0 in the accumulator. RTO, or retentive timer on, is the instruction you would want to use if you instead wanted to know the answer to the question, how long have I waited? So T on is have I waited long enough. Retentive timer on is how long have I waited. This sort of instruction would be good for, let's say you wanted to know whether or not a store clerk spent the majority of their time behind the desk. Their job is to, in this case, different stores do it differently, but in this particular instance, the job of the clerk is to stand behind the desk, greet the customers, and to help them purchase whatever they want to purchase. So he or she should always be behind the desk at all times. Well, let's say though that you're concerned because you drive by from time to time and it looks like they're in the back room, they're never out front. So you decided to set up a little test. And you put a sensor underneath the floor mat to detect if they were standing behind the desk. And they usually work an 8-hour shift. That's the shifts that you have set up. You're the store owner. And so as long as they're standing on the mat, this rung in condition is true. Well, that means this accumulator will continue to accumulate the time. And if they step off the mat, it just pauses the timer. So if this rung condition in becomes false, it doesn't reset it like the T on did. Instead, it just pauses where it's at. And then they step back on the mat, and this rung in condition becomes true, and the accumulator continues to accumulate. So then at the end of the day, you go and look at how much time had accumulated in this retentive timer on. That's why it's called a retentive timer on. It retains the amount of time that has been on. You go and look at the amount of time and you can tell how long total they have standed behind the desk. So this answers the question, how long have I waited, where T on answers the question, have I waited long enough? We're not going to go over the operands again because they're precisely the same as the T on instruction. The timer is supposed to be a timer structure. The preset is the target amount of time. So for your store clerk, that would be 8 hours, but you have to specify in milliseconds, so you'd have to do the math to convert that. And then your accumulator is the total time that has elapsed since this, it's the total time that this rung in condition has been true. The done bit will come on when the accumulator is greater than or equal to the preset. However, the difference is when the rung in condition goes off, it will not reset the accumulator. So we've also already looked at the timer structure. This is the exact same. We can programmatically set the preset by moving a value into the .pre attribute in the timer structure. We can access how long you've been waiting by reading the .acc attribute in the timer structure. And we can also look at the done bit, timer timing bit, and the enable bit in the timer structure as well. Sometimes that's helpful because if we want to know if the rung in condition is true, rather than duplicating all of the conditions for the timer, we can just look at the .en bit. The timer timing is similar, but it's only true until the done bit comes on. So the execution of this when rung in condition is false, the enable bit will be cleared to false and the timer timing bit will be cleared to false. It does not clear the accumulator. If the running condition is true, we've already discussed what this timer does, but if you wanted more or more precise information, you could refer to the manual and you could look at the flow chart to see precisely how Allen Bradley themselves describes this instruction to work. So now let's look at the timing diagram for the retentive timer on. If you remember, we saw that the timer on delay would reset the accumulator value after the rung-in condition becomes false. Now, let's look at and see how the retentive timer on works. So first of all, notice at the beginning the rung-in condition is false. Since the rung-in condition is false, the timer is not enabled. The timer timing bit was false because you weren't accruing time and you were not yet done. So the preset value, which is here, had not been met. Then the rung-in condition becomes true and it stays true for that pulse. So while the rung-in condition is true, the enable bit is also true. While the rung-in condition is true, the timer is timing. However, notice the rung-in condition becomes false. So this is like the store clerk stepped onto the mat, but then they stepped off the mat. And so the timer was not enabled. You're not timing because the store clerk's not on the mat. So we were accruing time, we were accumulating time, and while the store clerk was on the mat, and then they stepped off and we went flatline. Then they stepped back on the mat right here, and they stayed on the mat till here. So we were enabled and we were timing until they stepped off the mat, and then we became not enabled and we stopped timing. So while they were on the mat again, we started again accumulating time. Notice though, like I said, it's important. When the rung-in condition became false, we did not reset the accumulator. It just stayed where it was. That's the big difference between a T-on and an RTO. So we were here. The store clerk had just stepped off the mat again. While he was off the mat, you decided that you were going to reset the timer. We'll discuss how that works and how to use a reset instruction later on in the lecture. But suffice to say, it resets the timer. It sets the time to 0 and clears the enable and the timer timing and all those sort of things. So it reset the timer. So the accumulator dropped to 0 immediately. Then the store clerk comes back in, steps on the mat. So we were accumulating time. Steps off the mat, stop accumulating time. Stepped on the mat, started accumulating time. And this time we met the preset. So now he has been on the mat for 15 minutes straight. And if he's been on the mat for 15 minutes straight, you're supposed to come out and tell him he's doing a good job. So when the accumulator meets the preset, we stop timing. We do not accumulate anymore. That's important. Okay? So our instruction was still enabled, but we were not continuing to accrue time, to accumulate time. So let's say that you wanted to accumulate up to 15 minutes in this retentive timer on. Well, then you need to make sure that the value you enter for the preset is more than 15 minutes worth of milliseconds. So if you want to be able to accrue 15 minutes in your accumulator, you need to make sure that whatever you type in your preset is greater than 15 minutes times 60 seconds times 1,000 to get to milliseconds. So make sure you understand that. If you want to be able to have something, act as a stopwatch, then whatever amount of time you want your stopwatch to work up to, whatever the maximum amount of time you want to be able to time is, better be less than your preset. So make sure you set your preset appropriately high. So of the 4 instructions that I identified, T on, RTO, the next instruction to be discussed is the count up, or CTU. Now RTO and T on are both timers. CTU is a counter. Counters and timers are very similar, as I've mentioned, and you may notice right here in the format of this counter that it looks a lot like what we saw with the counters, or looks a lot like what we saw with the timers. The big difference is, rather than having a timer tag that we have to type in, it has a counter tag. So just like there's a timer data type that contains all the information for a timer, there is also a counter data type that contains all the information and is the memory housing location for a counter. So the data type is called counter, and you must type in the name of a counter data type tag in this operand location. Just like with timers, the preset and accumulator in these specific locations are immediate addressing only. The term immediate addressing comes from assembly. So assembly is the language that computers actually speak. So when something says that it has immediate addressing, or that the format is immediate, that means you must type in a value. So we're typing in a value for the preset, just like we typed in a value for the preset of a timer. The difference is the value for the preset of a timer carries the units of milliseconds. There is no unit for counter, just however many or whatever item you're counting. If we're counting rabbits, then this is rabbits, So we have the preset and accumulator operands, which will default to 0. So if you're wanting to count up to a certain amount and then have the done bit come on to tell you that you have met that amount, you'll need to set the preset appropriately. So these operands should be very reminiscent and should be very similar in your understanding to how the operands of a timer work. The counter structure is a little different than the timer structure. So there is a CU, which is a count up enable. That's the same thing as the .en attribute in the timer structure. That just tells you whether or not the rung in condition is true the last time the counter instruction was executed. The DN bit is the same in a counter as it is in a timer. The DN bit is on if the accumulator is greater than or equal to the preset. Overflow means that you've counted so much that whatever upper limit there was for the data type of the accumulator, you have blown past. In this specific instance, the data type of the accumulator is a double integer, a dent. The maximum value for a double integer is 2 billion and some change. So if you count past 2 billion, then you have overflowed and the .ov will come on. If you count down using a countdown counter, which we're not going to be using, but if you did, you could count down to the point where you underflowed. So you went so low that you went below the negative 2 billion and some change mark. That brings us to the preset and the accumulator, which are the same thing as the preset and the accumulator in the timer structure. However, as I've said, these do not come with the millisecond units. These are just whatever you're counting. So the preset is useful because you can programmatically set the preset, just like I said with timers. So let's say that you wanted to be able to have someone type in the value in the HMI that was going to wind up being placed into this preset for the counter. You could point the HMI at this .pre attribute of the counter structure, and they would be able to enter whatever the preset should be for this counter. So the accumulator is also a handy thing to be able to access programmatically, because you might want to do something like this. Maybe you're going to use the done bit, but maybe you don't want to use the done bit. Maybe you want to have logic that's something like this. So GEQ greater than or equal to, and we have a counter tag called my CT. Well, then all you'd have to do is say my CT dot, I'm going to need more room. My CT dot ACC, and let's say you want to know if you've counted past 10. So what this does is turn on some bit called my bit. You're turning on some bit called my bit whenever the accumulator, which is a part of the counter tag structure called myCT, goes to the value and greater than the value 10. So as you count up, if the value in the accumulator were to reach 10 or anything past 10, then this would be true and you would turn on my bit. So it can be helpful to directly access the accumulator, and it can also be helpful, as we've looked at previously, to directly access the preset to be able to set this target value. If the rung-in condition is false, then we are going to set the count up bit to false and do a couple other things which are described in the flowchart. And also the rung-in condition execution is described in the flowchart. But the general idea is that if the rung-in condition is true, then you will count up one time. That's a little different than a timer. A timer, as long as the rung-in condition is true, you're going to accumulate time. So if the rung-in condition is on for 2 minutes and your preset is 3 minutes, then the accumulator value will be 2 minutes worth of milliseconds. That's not true with the rung-in condition for the count up instruction. The count up instruction detects rising edges. So if you think about it logically, think about what you would really want from a counter. Would you want it to continue counting forever? So someone is placing parts into a bin, and there's a sensor to detect when their hand reaches into the bin to place a part. And you connect that sensor to the rung of a count up instruction, and someone reaches their hand down into that bin. Do you want it to count one time? Or do you want it to keep counting up as long as their hand is in the bin? Well, obviously the answer is you want it to count up one time. So the count up instruction detects a rising edge of the rung-in condition, and it will increment the counter accumulator 1. And so then the person's hand must be brought out of the bin, so the rung in condition will become false before it will count up again. That's a big difference between counters and timers, is the rising edge detection. To make that a little more clear, let's look at the timing diagram for this counter. So here we have the preset, which is set at apparently 1, 2, 3, 4. So our preset is set at 4. So in order for the counter to count up 4 times, we're going to have 4 rising edges. So the rung in condition is false, which means that the count up enable is false, and the done is not on because our accumulator is not greater than or equal to our preset. The rung in condition becomes true, which means that the count up enable becomes true. And it detects that rising edge. So right here we go from low to high. That's a rising edge. So it detects that rising edge, and the value in the accumulator goes up by 1. But notice the rung in condition is still high and we're not counting up. That's because we only count up once for each rising edge. So then we have a falling edge. So this is the person took their hand out of the bin. So they reached their hand into the bin to pick up a part, and then they pulled their hand back out of the bin. So we're not counting. We only counted one time because there's only been one thing that's happened. The person has reached into the bin one time and pulled out one part. Oh, they reached in again, right here. So here the rung in condition became true again. So whatever it is we're counting, in this case we're pretending that this counter is connected to a sensor in a bin. So whatever it is we're counting has just happened again. And so we increment our counter by 1. So this is the accumulator that we're incrementing. So it went up, then it happened again, so now we're at 2. It stayed true, but we didn't count up because we're detecting rising edges. Then it went off. We still didn't do anything other than turn off our count up enable. And then when it goes on again, we count up. Same song and dance, still on, but we're not counting up anymore. Goes off, and then it comes back on, so we count up. We detected another rising edge. So now, at this point, we have met the value in our preset. Our accumulator is now greater than or equal to the preset, which means our done bit becomes true because we have now reached the preset value. Now here's the difference between counters and timers. Another difference. Counters detect rising edges. That's one difference. Counters use a counter structure. That's another difference. The third difference is the counter will keep counting even after you've met the preset. So remember, with our retentive timer on and with our T-on instruction both, whenever we met this preset, we would not continue to accumulate any more time after that. With a counter, that's not how it works. Once you've met the preset, we went back off right here. But then, when the person reached their hand into the bin again, we counted up further. We'll just keep on counting. So that's the 3 major differences between counter and timer. Counters detect rising edges. Timers do not detect rising edges. They continue to accumulate as long as the rung in condition is true. Counters use a counter structure. Timers use a timer structure, which means timers work in milliseconds. And finally, counters keep counting after they've met the preset. Timers stop accumulating once the accumulator reaches the preset value. Now that we've looked at the T-on instruction for timers, the RTO instruction for timers, and the CTU or count up instruction for counters, let's look at how to reset those instructions. More accurately, we're going to look at how to reset the structures that you have to associate with the instructions. So remember, we had to type in the name of a timer tag to the TON or the RTO, and we had to type in the name of a counter tag to the CTU. Very similar in that nature. Well, we can reset the contents of those structures using the RES instruction, which is very faint, but you can see what it looks like right here. It looks like an if-else coil with the word the letters RES in the coil. So you would associate this reset with a tag. And that tag can either be of type timer, counter, or control. Don't worry about control. We're not going to talk about it. Timer and counter. So we can associate this reset instruction with either a timer or a counter tag. When the rung-in condition becomes true, we are going to set the value in the accumulator to 0, and the enable bit is going to become false. Well, all of the status bits are going to become false. If the structure is of type counter, we will set the accumulator value to 0, and we will set all of the status bits to false. In a second, we're going to look at what this looks like in ladder logic. But first, just a disclaimer, sometimes it's a bit easier or more convenient just to move the value 0 into the accumulator. That's what the reset does, as well as resetting the status bits. Specifically for counters, sometimes it's simpler just to move 0 into the accumulator. Two different ways to go about the same thing, resetting the counter structure. Now let's look at what counters, timers, and reset instructions look like in ladder logic. In a moment, we're going to do a practical where I program just a bit with counters and timers. But first, here's an image that we're going to dissect and talk about. So, someone has written some lines of ladder logic where we have limit switch 5. Limit switch is a general term used in industrial programming, which means a switch that detects the limit. It's a brilliant name, I know. So limit switch 5 is a terribly unimaginative name, but what they're conveying is this is some switch on some machine, and when that switch is on, we are going to count up. How many times? How many times are we going to count up each time this switch comes on? Yes, exactly 1 time, because for every rising edge of this switch, we will count up once. Now, every counter instruction, this is a counter instruction. The CTU is a counter instruction. Every counter instruction must have a counter structure tag. The counter structure tag for this particular instruction is counter_4. So if we went into the tag table for this program, we would find a tag called counter_4, and it would be of type counter. Now, they've typed in the immediate value 10 to the preset, and they've already counted 1. So you don't have to type anything into the accumulator for any of these, for either the counter or for the timer. The accumulator is telling you how many it has accumulated. Yeah, you could adjust it. You could type in a value here if you wanted to say start counting from 5 instead of 0, but that would be a bit odd and unusual. Typically, you'll type in a value to the preset, and you look at the value in the accumulator to see how many you have counted. So each time limit switch 5 comes on, the accumulator attribute, which is a part of counter 4, will increment by 1. So far, limit switch 5 has came on 1 time. If the accumulator value reaches the preset value, then this done bit will come on. So we can use this done bit in our program somewhere else to be able to make a decision based on whether or not we've counted up 10 times. Notice, putting something over here to the right of the count up instruction does not ensure that we have met the preset, does not ensure that the counter is done, because the output rung is not controlled by the done bit. The output rung, the rung condition out, is controlled by the count up enable. The count up enable is true if the rung in condition is true. Okay, so putting something to the right of a counter or to the right of a timer does not mean that that thing will occur when the timer or counter is done. You have to use the done bit to do that sort of thing, to accomplish that functionality. Okay, so that's what the first rung does. Second rung, limit switch 6. Another limit switch, which is going to control the state of the rung condition in for this T on instruction. T on instructions answer the question, have I waited long enough? How long are they trying to wait? Well, they're trying to wait 180 milliseconds because the preset value is the target amount of time that they are attempting to wait. So 180 milliseconds is what they've typed into the preset. So when limit switch 6 has been on for 180 milliseconds, the accumulator will accumulate 180 into it, and at that point, the done bit will come on. So just like our counter had a counter structure tag, our timer, our T-on timer, must have a timer structure tag. And this timer tag is called timer_1. And if we went to the tag table for this program, we would find a tag called timer_1 of type timer. If we looked at the preset or the .pre attribute of the timer_1 tag, we would find the value 180. If we looked at the .acc attribute of the timer_1 timer structure, we would find the value 0. So again, if we wanted to have something occur when we had waited long enough, then we would have to use this done bit in our program. And we would do so by typing in timer_1.dn. That is a Boolean tag, and we can use it on a contact, a normally open or normally closed contact. Anywhere you would use a Boolean, you can use the timer_1.done. So the name of the associated timer structure dot followed by whatever attribute you wanted to access. We're not going to talk about the bit shift instruction. That's a more advanced topic and not something that you run into very much. So we're going to skip to the resets. Everything I said more or less about T-on would also be true for RTO. The only difference between T-on and RTO is that the RTO instruction will not reset the accumulator when the rung in condition becomes true. So T-on, the moment this rung in condition becomes false, accumulator gets reset to 0. RTO, when this rung in condition becomes false, accumulator keeps or retains whatever value it currently has. That's why it's called the retentive timer on. The reset instruction can be used to set the accumulator to 0 and clear all of the bits which are inside this counter structure or inside a timer structure. So whenever limit switch 8 comes on, we will clear the accumulator in counter 4 and set all of the bits inside counter 4 to false. Whenever limit switch 5 comes on, we will set the accumulator inside timer 1 to 0, and we will clear all of the status bits inside of timer 1. So .done will be cleared. The enable will be cleared. Everything will be cleared. Now, I mentioned that sometimes with counters specifically, it can be easier to simply move 0 into the accumulator than using the reset instruction. The reason that it is sometimes easier to just move 0 in for counters is because of the way they execute. If you were to look at the flowchart, it says that it does a rising edge detection. But the way that it does a rising edge detection is that if the rung-in condition is true and the count up enable is false, so this bit is a memory of the last time this instruction executed. So if in scan 1, this limit switch 5 is off, so the rung-in condition is false, it will set the count up enable to false. And then we finish scanning the program and come back around, and okay, we're back at the top and we're scanning this rung again, but now limit switch 5 is true, so the rung condition in will be true. It will say, is the rung condition in true? If yes, is the count up enabled true? If the answer is no, then it will count up, because it's detecting that last time it scanned, the rung condition in was false. And this time, the rung condition in is true, so it has detected a rising edge. And the way it detects that rising edge is by using the count up enable as a memory of the last scan. So if count up is not true and the rung condition in is true, then there's a rising edge. That's the logic it uses, and it will increment the accumulator by 1. Fantastic. One problem. Whenever you use this reset, it's going to make the count up enable false. So then, if limit switch 5 is on, when you reset it, when you reset this counter, then what's going to happen is we reset the counter, it moves 0 into the accumulator, and sets the count up enable bit to 0. And we finish this scan, come back around and begin to scan again. And limit switch 5 didn't just now come on, it's been on for 5 minutes. But the rung condition in is true, and the count up enable bit is false, so the instruction thinks that it has found a rising edge and it will increment the counter back to 1. It's a very common mistake with count up instructions and the reset instruction. So it's important to make sure before you reset the counter, you should always check that the counter 4.cu is false. Or some sort of logic very similar to this, so that when it scans back around to the top, it doesn't immediately count up 1 simply because you have reset the count up enable bit through the reset instruction. Another way to get around this, simply use a MOV instruction to reset the accumulator when using a counter. So why is that not a problem with timers? Hopefully you guessed it, because timers don't detect the rising edge. As long as the rung in condition is true on a timer, then the accumulator is accumulating. On counters, the counter only counts up 1 per rising edge. So this isn't quite a bug, it's just something that you need to be aware of. Either you need to protect yourself against the situation where you accidentally count up because you reset while the rung in condition was true, or you can just simply use a move 0 into the accumulator to reset counters. Okay, so let's take a quick practical look at how to use timers. So the first thing we're going to do is just debounce a button. So let's create a tag to use for our button. We'll call it button, fancy name. And it needs to be a type bool because it's a Boolean tag that we're going to have. Then we need the timer that we're going to use to debounce it. So button, dbnc for debounce, and then tmr for timer. And we have to have it of type timer. Now let's take a quick look inside this timer structure tag. See, it's of type timer to see what's inside. So inside here we see the preset, which is the target that we're going to time up to, but we won't time past that. So our accumulator will never be any greater than the preset, but it will be equal to the preset, and once it gets equal to the preset, we will turn on done. So done is a bool, as is timer timing and the timer enable. The timer enable is true if the run condition into the timer instruction that we associate with this timer structure is true. All right, let's use it to turn on button is debounced, and that's a bool tag that we will turn on when the button has been on for a time greater than or equal to whatever time we set in the preset. All right, so first of all, we're going to have some condition and then a timer that we will have time when that condition is true. And that's just how we would go about that. Now we're using a T on because we want to know the answer to has it been on long enough. And what is it we want to know if it's been on? We want to know if the button's been on. So when we're populating the operands for a T on instruction, the first thing we have to do is give it a timer tag. So let's start typing. Oh, as soon as we typed in BU, it said, oh, I know of a timer tag that starts with BU, and it recommends it. If this is correct, good. If not, you can click this arrow and go and find the tag that you want to associate with this timer instruction. Now we need to specify the preset, and we do not need to specify the accumulator. That's how much time has passed. So we want to be able to see this happen, so something like 100 milliseconds doesn't make sense. We need something longer. So 1,000 would be 1 second because 1,000 milliseconds is 1 second. So let's do 10,000 for 10 seconds. 1, 2, 3. So there's 1 with 5 zeros, or 4 zeros. Yep. There's 10,000 milliseconds, which will be 10 seconds. So when button is on for a time greater than or equal to 10,000 milliseconds, 10 seconds, done will become true. To be able to use that fact, what we need to do is create a contact and associate it with that done bit. Well, how do we do that? Very easy. So the name of the timer tag right here, button debounce timer, button underscore debounce timer, and then to access an attribute inside that structure, you use the dot operator, the period operator. So period, and then it says, oh, you want to access one of the attributes? How about the preset? Nope, we don't want that. We want the done bit. There it is. So when the done bit is on, we want to turn on button is debounced. Perfect. So now let's download this code and run it and see how it works. So we had to create the tag that we were going to associate with our timer instruction, just like we talked about in the lecture. Yes, we want to return to remote run. Okay, we're running. Now our accumulator is at 0 because the rung in condition is false. And whenever the rung in condition on a T on instruction is false, it resets the accumulator. So let's do Control T to toggle this bit. Oh, okay, now our accumulator is running. So these are milliseconds, the amount of milliseconds that have passed. And we've waited 10 seconds, so our button is debounced is now on. Simple enough. So this bit came on when the accumulator reached the value in the preset. If we turn this off, the accumulator will immediately go to 0 and our done bit will reset. There we go. Now, what if we wanted to adjust this preset value in a program? So let's do that real quick. Let's go offline and adjust our program so that we can do that. So what we want to do is we want to have a move instruction where we move, let's do 500 into the timer tag, which is button underscore debounce timer dot, and what we want to do is set the preset. That's the target. So we're going to adjust the preset using code rather than typing it in. I could have done this as an online edit, but I chose to download again. Okay, so first of all, notice the run condition into the move instruction is true, so it's moving the value 500 into our button debounce timer preset, and notice up here it changed the value that's displayed for the preset on the T on instruction. So this is how you could adjust the preset value using code rather than typing it in. Okay, so now let's do a quick counter demonstration. I'll leave the retentive time on for you to figure out. We'll go offline, do a download again. So let's delete what we have. We'll leave the rung, but we'll delete the contents of the rung. The first thing we need to do is go back in and adjust the tags. So we want to know this time is how many times a button has been pressed. Total button pushes. And we're going to save it in a double integer. So this will be the number of times that we push a button. And this will be our counter. Button CTR, button counter. And it has to be of type counter. It told me that by changing the data type, it was going to lose some data. That's okay, I didn't want the old data. So now we want to have our button be the condition which allows our counter to count up. So let's give our counter instruction a counter tag to use as storage. There's button counter. Preset, we're going to set something just, who cares? We don't care. We're not counting up to a preset, so we'll set it at a really high number because we don't care. We're just wanting to keep track of how many. We're not ever going to be done. So button is going to control the running condition for this count up instruction, which will count up each time the button is pressed. Then we want to store. Now remember, you can use any instruction, you can insert any instruction and then type the name of the instruction you want to change it. So I want a move instruction because I want to store the total button presses in our total button pushes. And this counter is going to store the total button pushes in the accumulator. So to access the accumulator, all I have to do is go to the counter structure tag called button underscore CTR and then use the period operator to access the accumulator. So now what's happening is each time the button gets pressed, we will count up 1 and then we will move the value of our accumulator into some tag called total button pushes. Now let's also, just for fun, let's also reset this counter by moving a 0 into the accumulator. So move 0 into button counter dot ACC. And when do we want to move 0 in? We will move 0 in whenever we push the reset button. And there is no reset button yet. So let's create our reset button real quick. Reset of type bool. Okay, perfect. So now whenever we press this button, it will count up once. It will move that count into the accumulated count into total button pushes. And then whenever we are ready to clear the current count, we simply will turn on reset. What if we wanted to reset the count every time the total went above 5? Can you think of a way to do that? We'll do that in just a second, but be thinking about how before we do it. All right, Control T to toggle button. Okay, button is now true, count up enable is true, and it detected that rising edge. So the value became 1. We'll turn it off. Let's turn it on again. Okay, 2. And it increments count, and then every scan of the PLC, we are moving the value stored in the accumulator inside this counter tag into our double integer called total button pushes. Okay, now let's reset the total. Okay, we moved in 0, and so now our accumulator goes back to 0. Let's continue counting. Count. Each time I toggle it, it's going to count up once. Now let's clear this value while the button is pressed. No problem. What if, instead of using a move instruction, I used a reset? Now each time I push the reset button, it's still going to reset the counter, but instead of resetting it with a move 0, I'm resetting it with the reset command. So let's count a little. 1, 2, 3, 4, and we will leave button on, just like we did a second ago with the move 0, and this time we're going to turn on reset. Turn it off. Oh, look at that. It immediately counted up to 1. The reason is because it reset the count up bit and it thought there was a rising edge. That's why I said it's a lot of times easier to just use a move 0. So that's my preferred way to reset a counter. Button underscore counter dot acc, and we'll just move in 0 like we were. Also, now instead of using this reset bit, let's have it reset whenever the value in the accumulator goes above 5. So let's say GEQ to detect when something is greater than or equal to. So when the button underscore CTR dot accumulator is greater than or equal to 5, we will move 0 into the accumulator. Hopefully that logic makes sense to you. We want to reset the counter when it goes at or above 5, so we simply move 0 in whenever button counter dot accumulator is greater than or equal to 5. So let's begin to count. 2, 3, 4, 5. Oh, and immediately it resets it. So now we have shown how to programmatically access the accumulator, compare the accumulator, and reset the accumulator. And we previously showed how to programmatically set the preset value so that you could, write some sort of code to control how long a timer lasted.